Welcome back to the channel. We have a question here on work energy and power from November 2021. If you're new to the channel, please subscribe and let's start. The first question says state the principle of conservation of mechanical energy, right? It states that the total mechanical energy in an isolated system is conserved. That is the sum of the potential energy and the kinetic energy at a certain point it will always be equals to the sum of the potential energy and the kinetic energy at any other point is conserved. 5.2, it says use the principle of conservation of mechanical energy to calculate the speed of the box when it reaches point P. So let's have a look. The height at which it starts at is 5 meters, and then at point Q height is 0. It slides down, so velocity initial thereby a height of 5 meters is 0 meters per second, and at point Q is what you are interested in. So because we know that mechanical energy is conserved in an isolated system, we can use the formula we have here on 5.1 to calculate 5.2. Usually these questions are always like this. Whatever you define on the first question, you are going to use it to answer the question that follows. So EP, potential energy, is mass divided by multiplied by gravity multiplied by height. So that is going to give us 2 multiplied by 9,8 multiplied by 5 plus the kinetic energy at the top, which is 1 over 2 multiplied by 2 multiplied by 0 squared, because it's sliding down, so it's coming from stationary, right? This is equals to the potential energy at the bottom, which is 2 multiplied by 9,8 multiplied by 0, because now the height is 0, right, at point Q. And then we have plus 1 over 2 multiplied by 2, the mass, multiplied by VF squared. So there we have it. We are only left with one variable, so we can do a bit of math and rearrange the equation. So we're going to have 1 over 2 multiplied by 2 VF squared equals to 2 multiplied by 9,8 multiplied by 5 minus this expression here, which is going to fall off. That's just going to give us 0. The next step will then be to divide both sides by 1 over 2 multiplied by 2, which is just VF squared equals to this expression here divided by 1, because 2 multiplied by 1 over 2 is just 1. So we're going to have 2 multiplied by 9,8 multiplied by 5. We take the square root on both sides. We have the square root of VF squared equals the square root of 2 multiplied by 9,8 multiplied by 5. So we get V equals to, let me put that into my calculator real quick. I have 2 multiplied by 9,8 multiplied by 5, and then I take a square root. I get 9.899 meter per second. That's how you would determine VF at point Q. We stick into the conservation of mechanical energy. Let's go ahead and do 5.3. The question says, okay, the box passes point Q and moves 10 meters. on a horizontal surface before striking a barrier at point R at a constant speed of, oh no, not at a constant speed, at a speed of 4 meters per second. Use energy principles to calculate the magnitude of the average frictional force on the box as it moves from point Q to R. So we have our box there. We have a normal force that is always acting, assuming the object is on the surface, and we have gravity that's always acting, period. And then we have frictional force that is opposing the motion, and then that's about it. Frictional force is the only non-consecutive force we have that's doing any work. So sticking to the energy principle, we have work net, which equals to change in kinetic energy. We already know what the change in kinetic energy is, because we have VF and VI, right? So that would give us work done by friction, because work done by Fg it's 0, and then work done by normal force is also 0. So we just have work done by friction. This will give us 1 over 2 m Vf squared minus 1 over 2 m Vi squared. Here for work done by friction, we can then break it down, and then we have frictional force multiplied by delta x multiplied by cos of theta equals to 1 over 2 m Vf squared minus Vi squared. So we have Fr multiplied by 10 meters multiplied by cos of 180 degrees equals to 1 over 2 multiplied by 2 kgs. Vf when it strikes R, when it gets to R, is 4 meters per second, right? So we're going to have 4 squared, and then Vi at Q is what we calculated above, 9,899 squared. That will, so now let's make Fr the subject of the formula. We are gonna get Fr equals to 1 over 2 multiplied by 2 4 squared minus 9,899 squared. The squared is inside the bracket, divided by 10 multiplied by cos of 180 degrees. Let me just put that into the calculator real quick. We have 4 squared minus 9,899 squared divided by 10 multiplied by minus 1. So Fr in this case will be 8,2 newtons. Let's move to 5.4. So we have 5.4. As soon as I see the word impulse, I'm thinking F net equals to delta P divided by delta T. In this instance, it's been said that there's an impulse of 14 newtons by second to the left, right? So if you're taking the right as positive, then the left will be negative. Let's do that. So we're gonna have minus 14 equals to delta P divided by 1. Delta P is 14 newtons multiplied by second, and if you solve this is what you get, right? Let's make delta P the subject of the formula. We're gonna have delta P equals to minus 14, and then what is delta P? Delta P is mass velocity final minus velocity initial equals to minus 14. We know the mass of the object is 2 kg. We know the velocity final is what we're looking for, and the velocity initial is our previous velocity final. So this will be 4 meters per second equals to minus 14. If we divide both sides by 2, we get Vf minus 4 equals to minus 7. Take 4 to the other side, we get Vf equals to minus 3 meters per second. But then Vf is not the only thing we are interested in. We're interested in the change in kinetic energy. So that will be change in Ek equals to 1 over 2 m Vf squared minus Vi squared. 1 over 2, the mass is 2 kg. Vf squared is minus 3, which is going to get squared, so the negative sign is going to disappear. So we have minus 3 squared minus V initial squared, which is 4 squared. Let me put that in my calculator real quick. Actually, let's just solve it. This will give you 1. This will give you 9, and then this will give you 16. 9 minus 16, that is minus 7. So we have minus 7 joules. Yeah, and that's it for the equation. Thank you for watching. Don't forget to like and subscribe and go through the channel. There's a lot of other nice videos. We have a question here on work, energy and power from the final examination, November 2020. The first thing I like doing is reading through the question and jot down all the information I think would help me in answering the question. So I'll just go ahead and do that. So it says a roller coaster car of mass 200 kg. So I'm gonna jot down the mass we have is 200 kg. With the engine switched off, travels along track ABC, which has a rough surface. So I know that there's some frictional force because it's said to be a rough surface, as shown in the diagram below. That's the diagram right there on the left. At point A, which is 10 meters above the ground. So we have point A, which is 10 meters above the ground. The speed of the car is 4 meters per second. So we have V equals to 4 meters per second. At point B, which is a height H. So at point B, we have a height which is unknown, X meters, so to say. The speed of the car is 2 meters per second. So we have V, which equals to 2 meters per second. During the motion from point A to point B, 3.4 times 10 to the 3 joules of energy is used to overcome friction. So work done by friction or to overcome friction is 3.4 times 10 to the 3 joules. The first question says, define the term non-conservative force. So we have conservative and non-conservative force, right? So let me write that down there. Conservative force. The work done by a conservative force is independent of the path taken. Independent of path. And as you have guessed, non-conservative force, non-conservative force, the work done is dependent of path. Work done dependent of path. Let me just write that down. There we have it. So the question says non-conservative force. So you would write that the work done by a non-conservative force is dependent of path forces like friction. 5.2, calculate the change in kinetic energy of the car after it has traveled from point A to B. This is quite straightforward. So point A is our starting point and point B is our ending point. At point A, like we jotted down when we were writing the given information, we have 4 meters per second, and at point B, we have 2 meters per second. So we know that kinetic energy is given by 1 over 2 mv squared. The change in kinetic energy, which is what we're interested in, is given by 1 over 2 m velocity final squared minus velocity initial squared. The mass is given as 200 kg, so we're going to have 1 over 2 multiplied by 200. Vf is 2 meters per second, so we're going to have 2 squared subtracted by 4 squared. 1 over 2 multiplied by 200, this is just going to give us 100. And then 2 squared, that's 4. This 2 is not on the outside, it's on. And then we're going to subtract 16. This is just going to be 100 multiplied by minus 12. So this is minus 1,200 joules. So that's the change in kinetic energy, minus 1,200 joules. Let's move ahead and go to 5.3. Use energy principle to calculate height h. There's 3 equations that should come to your head when you hear energy principle. Is that E, mechanical energy, the mechanical energy at some initial point is equals to the E, mechanical dot at some final point. The other energy principle is that work net is given by change in EK. Work non-conservative is given by change in EK plus change in potential energy, EP, right? So whenever we have a question that is saying use energy principle, we're going to use one between the 3 of these equations. If you use any, we are going to get the answer. Actually, I'm going to use the first one, and I'd ask you guys to try using the other equations and post your answers in the comment. So E mechanical energy initially, we have EK, which is the kinetic energy, and then we have EP, which is the potential energy, and then this is sort of an unusual case because we have friction that is opposing. So here we're supposed to also have the work done by the friction, like we stated there, right? And then on this other side, there's nothing about the rough surface, so we are going to have energy kinetic plus energy potential only. So if we didn't have friction while going down from point A, then we were not going to have this work done by friction, right? So let's go ahead and sub that. At point A, we know that we have 1 over 2, 200 kg. The velocity is 4 squared plus EP, that is mass, which is 200, multiplied by gravity, which is 9,8, and then multiplied by the height, which is 10, plus the work that is done to overcome the friction. It is given as 3.4 times 10 to the 3 joules. But then because friction opposes the motion, we're supposed to put it with a minus sign, right? That is negative work. So we're going to have minus 3.4 times 10 to the 3 equals to EK at point B, 1 over 2. The mass is 2000 kg, the speed is 2 squared, plus mgh, the mass is 2000, or 200 I meant, gravity is 9.8, and the height is what we are interested in. So sorry for that, let me just bring that back. There we have it. Let's move ahead. So now we basically done with the physics. We sort of now doing the math, right? So let me put everything on the left hand side on the calculator and see what we have. So we're going to have 1 over 2 multiplied by 200, the velocity squared plus the potential energy multiplied by 10 minus 3.4 times 10 to the 3. On the left hand side, we're going to have 17,800, and then on the right hand side, we're going to have 1 over 2 multiplied by 200 will give us 100. 100 multiplied by 4, this is going to give us 400, plus let me put that in the calculator. 200 multiplied by 9.8, 1960 multiplied by 8. We're going to take this 400 to the other side and divide by 1960. So this would imply that our height is 17,800 minus the 400 we talked about, divided by I'm so sorry for that, divided by 1960, right? Let me put that in the calculator. We have 17,800 minus 400 divided by 1960. Our age is therefore 8.8775 meters, right? Which makes sense. Point B looks to be slightly below point A. Let's move ahead. Like I said, please use this equation, use this other equation too, and tell me if you get the same thing. You should get the same thing. 5.4. On reaching point B, the car engine is switched off. It's switched on in order to move up the incline to point C, which makes sense, which is 22 meters above the ground. So we know that we have a height of 22 meters above the ground at point C. The car travels for 15 seconds, so we have t equals to 15 seconds. The speed is constant, is given as 2 meters per second. Average frictional force is given as 50 Newton. The question says, calculate the power delivered by the engine to move the car from point B to C. So what is power? Power is the rate at which work is done. So that will be work divided by T. If you remember, we had an equation above that says that work done by non-conservative forces is equals to the change in kinetic energy plus the change in potential energy. So what are the non-conservative forces that are acting on the object? We have the work done by the engine, which is dependent of the path, and then the work done by friction, and then change in EK is 1 over 2 m VF squared minus VI squared. plus mg h final minus h initial. So let's go ahead and sub that. Work done by the engine is what you're interested in, so we're gonna have work done by engine plus work done by friction. The constant frictional force is given as 50 newtons, so we're going to have 50. And then the question to ask is, what's delta x? If you read the question attentively, it is said that it travels for 15 seconds, right, at a speed of 2 meters per second. If you remember from grade 10, distance is given by speed multiplied by time. So we're going to have 2 multiplied by 15, which is equals to 30 meters, right? So that's what we're going to put in there. So we're going to have 30 meters. Cos of 180, that's always the angle for friction, equals to, let me just erase that real quick, equals to changing kinetic energy. So we have 1 over 2, 200, the velocity final is 2 meters per second minus the velocity initial 2 meters per second squared, because it says it is moving at a constant speed, right? And then the change in potential energy, we have the mass of 200 kg, we have 9,8 for gravity, height final is 22, height initial is what we calculated, 8.8775, 8.8775. I hope you can see that. So now let me put these numbers in the calculator. We have 50 multiplied by 30 and then multiplied by -1. This is just gonna give us minus 1,500 equals to, and then now I do the right hand side. The changing kinetic energy is gonna fall off, so there's no need to put that. Minus multiplied by 9,8. The change in height 22 minus 8,8775, and then this gives us 25,720.1. So work done by the engine equals to 25,720,1 plus 1,500. You add that to and you get, let me do that real quick, plus 1,500, you get 27,220.1 joules, right? The SI unit for work. And then let's move ahead. Then the question said the power done by the engine, right? So we're going to have the work, which we just calculated, 0.1 divided by the time in seconds, it's 15 seconds, and that gives us, just wait a second, let me put that in the calculator, 27,220.1 divided by 15, that gives us 1,814.67 joules per second, or watts, right? That is it for this question. You can play it back, try doing these questions by yourself before you see how I do it. The question you might be asking yourself right now is, when do we use which equation? And that's a very valid question. I think that's the difficult stuff to figure out. I'm going to do a separate video on that, so make sure you subscribe so that you don't miss out. A force of 62.5 Newton is applied to a trolley of mass m kg parallel to the inclined surface as shown to keep it moving down an inclined surface at a constant velocity. the vertical height of the inclined surface is 12 meters. And then refer to the diagram below. A kinetic frictional force of 35.5 Newton acts on the trolley as it moves down the inclined surface. And then 5.1 says write down the name of the conservative force acting on the trolley. So in our context, in our curriculum, we only have two conservative force that we talk about, right? We talk about gravitational force and electrostatic force. Here in this instance, the only force that is acting on this trolley as it moves down the incline at a constant velocity is gravitational force, right? Gravitational force. And we can move to 5.2. 5.2 says let's calculate the work done by the friction on the trolley, right? So fine, we are given the frictional force. Here it is. Here it is said to be so we have frictional force which is equals to 35.5 newtons, right? And then apart from frictional force, we know the height, right? But then from the height we can find the length of the incline, right? How can we do that? We have the angle here, and then we have the height. We can use trig ratios, right? So what we can do, we can say that sine of theta is equals to y divided by hypotenuse, right? But then in this instance, we know the angle. We know that sine of 30 degrees is equals to our y is our height, right? Which is 12 meters. So we have 12 meters divided by the length of the incline. That's what we ultimately interested in. So we can label that as delta x. So it should become easy to see now that delta x will be equals to 12 divided by sine of 30. And then if we do that, we get 24 meters. So we have the frictional force, we have delta x, and then we have the angle between the frictional force and the direction of the motion. So now we can say that the work done by the frictional force will be equals to that force of friction multiplied by the displacement of the object multiplied by the angle, right? So what is the frictional force? We've already said that the frictional force is 35.5, right? We calculated the displacement, that's 24, and then the angle. All the time, frictional force opposes the motion, right? So the angle should be 180 degrees, right? So we have cos of 180 degrees. And then if you punch that in your calculator, you're going to get minus 852 joules, right? So that is the amount of work the frictional force is doing on the trolley. And then now let's do 5.3. 5.3 says write down the change in kinetic energy when the trolley reaches the bottom of the inclined surface. Let's go back to our statement again. We have constant velocity here, right? We know that the change in the kinetic energy is equals to a half mass Vf squared minus a half mass Vi squared. If we are moving at constant velocity, then Vf squared is equals to Vi squared. So the change in kinetic energy should be equals to 0 joules, right? And then now we can do 5.4. 5.4 says use the work energy theorem to calculate the mass m of the trolley. The work energy theorem to calculate the mass m of the trolley. Here I'm going to use work net is equals to the change in kinetic energy. The other formula you can use, you can say that the work done by non-conservative forces is equals to the change in the potential energy plus the change in the kinetic energy, right? Maybe this is the formula you might want to try out and see if it also works. But then I'm going to use this first formula here, right? So what is the work net? The work net is the sum of all the works done by the individual forces, right? So we have the work done by Fg, and then we have the work done by friction, and we have the work done by the force applied, right? And this is equals to Ek. But we know what Ek is. Ek is 0, right? Apart from Ek, we know the work done by friction. We just calculated it in 5.2, right? So what is the work done by Fg? The force of gravity multiplied by the height, and then cos of the angle, right? Plus the work done by friction. We know that that is minus 852, right? And then plus the work done by the force applied. We know that the force applied is 62.5, right? So we're gonna, let me just write it in the line below. So plus 62.5 multiplied by the displacement, and then cos of the angle, right? And this should be all equals to 0. So let's talk about this work done by gravity first. So there's two ways you can use to find the work done by gravity. You can use the gravity itself, right, and the height. Apart from that, you can find the parallel component of the gravity, and then you can use the displacement, right, the distance from A to B, which is 24 meters. If you also use that, we should get to the same answer, right? But then I'm just gonna use this in this question. So what is Fg? Fg is the mass multiplied by the gravity, right, which is 9.8, and then the height is there on our sketch. We know that is 12 meters, and then what is the angle? The angle between Fg and the change in the object's position relative to the height, right? That angle is 0, so we have cos of 0, right? Because gravity is pulling the object down, and ultimately along the height the object is going down, right? So that angle is 0, and then minus 852 from gravity, and then now we'll have plus 62.5, and then the displacement we calculated it, we know that is 24, right? 24, and then multiply by cos of 180. Why am I saying cos of 180? Because this force applied is pulling the object up, but then the object keeps sliding down at constant velocity, right? So the angle between the force and the direction of the motion is 180, and that will all be equals to 0. So you can see here that the only variable we have that is left is the mass, right? So we have solved the conceptual physics problem. Now we're just solving the math. Before I put anything in the calculator, I'm just gonna take everything that belongs to the right hand side to the right hand side, right? So I'm gonna have the mass multiplied by 9.8 multiplied by 12. Cos of 0 is 1, right? So there's no need to include that. That will be equals to, now I'm taking this minus 852 to the right hand side, so it will be positive 852, and then this here, right, we know fully well that cos of 180 will be minus, right? So when I take 65 multiplied by 24 to the right hand side, it should be positive, because cos of 180 is minus. Now we're taking it to the other side, it should be positive, right? So here we're gonna have plus 62.5 multiplied by 24. So now it should be easy to see. We're dividing both sides by the coefficient of m, right, the mass. So we're gonna have the mass being equals to 852 plus 62.5 multiplied by 24 divided by that coefficient 9.8 multiplied by 12, and the mass is apparently 20 kgs. Question 5 says a demolition ball is used by crane to break the wall of a building. The demolition ball of mass, so we have a mass there. Let me just write it down. A mass of 1250 kgs is lifted by the crane to a point R at a height of 5.8 meters. So we have a height of 5.8 meters. above its lowest position in 60 seconds. So we have some time t of 60 seconds. Ignore air friction. Okay. And then the first question, 5.1, says define the term power in words. So power, the formula for power is given as work divided by delta T. So from this formula, you can define power as the rate at which work is done. Right. 5.2 says calculate the average power dissipated by the crane in lifting the demolition ball to point R. Okay, the average power dissipated by the crane in lifting the demolition ball to point R. The height is to point R is 5.8 meters, right? We have already wrote that down. And then, okay, power average is given as force multiplied by velocity average. So what this question wants us to do is to determine the force, determine the velocity average, and then we have the power average. So the domain knowledge of a crane is that it moves at constant speed or constant velocity. It doesn't accelerate or decelerate at any point of the motion. So what that means is that the forces when the ball is moving up are balanced. Because it's hanging, we don't have normal force, frictional force, or any of that. The only force that's acting on the ball, apart from the force exerted by the crane, is force of gravity. So that is to say, F crane is equals to minus Fg, right? Because these forces are balancing out, and then the demolition ball is moving at constant speed. So that is equals to minus mass multiplied by gravity, and then the mass is we already have it, is minus, oh, it's actually not minus, the mass is 1250 kg, and then force of gravity minus 9.8, right? And then the minuses will give you a positive. And now let me put that in the calculator and see what I get. 1250 multiplied by 9.8, that is 12,250 newtons, right? And then now what's left is velocity average. We know from grade 10 that distance is given by speed multiplied by time. So if you make speed the subject of the formula, you get distance divided by time. The same is true about the velocity. So in this instance, our distance is the height, right? So we're going to have height, and then the time is the time, is the 60 seconds we have there. So this will give us 5.8 meters divided by 60 seconds, right? If we put that back into our equation, we'll get power average equals to 12,250 multiplied by 5.8 divided by 60. If I put that in the calculator, I get 12,250 multiplied by 5.8 meters divided by 60 seconds. That gives me 1,184.16 recurring joules per second, or watts, right? Let's move ahead. That was 5.2. Let's move to 5.3. There's some more information given that says the demolition ball is released from point R and strikes the wall at the lowest point of its swing. The ball then moves 0.25 meters horizontally into the wall before coming to a rest. So let's say 5.3, and then let's sketch that down. So we're moving from point R, and then we hit the wall. After we hit the wall, we move horizontally, right? That's what the information is saying. And then we come to a rest. So that is VF here, it's 0, right? And then this horizontal movement, that's 0.25 meters. And then this height here is 5.8 meters, like we already know. Okay, now the question for 5.3 says, define the term conservative force. A conservative force is a force in which the work done is independent of path. In our curriculum, the only forces that are conservative is natural forces, electrostatic, magnetic, and gravitational force. All other forces are non-conservative. They depend on the path taken. So a conservative force is a force in which the work done is independent of path. Let's move ahead. 5.4 says, is the force which the wall exerts on the ball a conservative or a non-conservative force? I already stated for 5.3 that the only conservative forces we have are natural forces. So a force that is exerted by a wall will thus be non-conservative. Yes. Let's move to 5.4. 5.4 says, oh no, 5.5 I meant, my bad. State the energy conversion that takes place during the downward swing of the demolition ball. The downward swing is from R until it hits the wall. And then they say we should ignore friction, right? Let's use mechanical energy. We have EP plus EK at the top is equals to EK plus EP at the bottom, right? At the top, it's stationary, so EK is 0. So we only have EP. And then at the bottom, we've exhausted the height. The height is now 0, right? So our EK is the only thing we have. The EP is 0. So the energy conversion is potential energy to kinetic energy, right? 5.6 says, using energy principle, calculate the magnitude of the average force exerted on the ball while it moves into the wall. If you've watched other of my videos, I always say that usually 5.3 helps you answer 5.4 and then 5.4, 5.5, so on and so on and so on. So let's go ahead and try and apply the same principle to this problem. 5.5, we see that at the top we have EP and then at the top we have EK. So if we can determine EP at the top to find EK, then we can find the velocity at the bottom, right? So here the V is 0 and here the V is the max, right, for that journey. So let's just call it V, let's call it V2, right? So if we use this formula that we have here, EP equals to EK, we can determine this velocity, right? And then maybe we can, see what we can do with that velocity. But then if you pay close attention, we have VF, we have this V2 here, and then we have the distance covered. So with that, we can calculate the acceleration of that motion, right? So we will have the acceleration, we have the mass of the object, and then we can just use F equals to MA to determine the force exerted, right? So, but then to find the acceleration, we first need to use this formula here to find V2. So let's go ahead and do that. We have EP equals to EK from 5.5. So EP is mass multiplied by gravity multiplied by height, which is equals to 1 over 2 mv. We're calling this 2, right, squared. So the mass 1250, gravity is 9.8, the height is 5.8, and then 1 over 2, the mass is 1250, and then we have velocity 2 squared. If I put the left hand side on my calculator, I get 71,050, which is equals to 1,250 divided by 2, that is 625 v2 squared, right? And then I can solve for v2 squared, so v2 squared will be 71,050 divided by 625, and then take square roots on both sides. I'll get v2 equals to, let me put that in the calculator, 71,050 divided by 625, that is 10.6621 meters per second. And then I'm gonna use these to find the acceleration for the horizontal movement here. All right. I think for clarity, I shall drag this down so that you can be looking at it while I'm solving it. So okay, let's see. Yes, so now we have v2. So we're gonna have we have v2, we have vf, we have delta x, right? And then we need acceleration. No, this is, yeah, what we need acceleration. So the formula to use here is vf squared equals to vi squared plus 2a delta x, right? Vf squared, it comes to rest, so it's 0. Vi is 10.6621 we squared plus 2. Acceleration is what we're interested in, and then multiply by 0.25. So we're gonna take this term to the left hand side. We're gonna get minus 10.6621 squared equals to 0.5 acceleration that I multiply by a, that's 2 multiplied by 0.25. So if you make a the subject to the formula, you will get, let me put that in my calculator real quick, 10.6621 squared, what's going on here, squared divided by 0.5, that is 7.36 meters per second squared, right? So now I have my acceleration, I have my mass, and I know fully well that F equals to ma. So m is 1,250, the acceleration is 227, there's a minus here, 227.36, and then if I put that in the calculator, I get, let me see, 1,250 multiplied by 227.36. I get minus 284,200 newtons. That's it for this question. I know it looks a bit complicated. Well, it is. So I'd advise you to rewatch the video again, just to wrap your head around what's going on.
A box is pushed from rest with a constant applied force of 30 Newton over a horizontal surface which has 3 different regions. Each region is 5 meters long and exerts a different frictional force on the box as it moves through. And then we have a diagram there that clearly demonstrates what the statement is saying. It goes on to say that the graph below shows the kinetic energy of the object as a function of the distance from the starting point as the object experiences the constant applied force of 30 Newton. The first region is from 0 to 5 meters, the second region is from 5 to 10, and the third is from 10 to 15. 5.1 says state the work energy theorem in words. The work energy theorem essentially says that work net is equals to change in EK. So what this is telling us is that the work net done on an object is equals to the object's change in kinetic energy. The work done on an object is equals to the object's change in kinetic energy. And then now we can move to 5.2. 5.2 says, use the work energy theorem to show that the gradient or slope of the graph represents the net force experienced by the object. I don't really like these questions that have to deal with graphs. But if you're doing physics, they're gonna come and you will need to know them. On the y-axis, we have EK, right? And then on the x-axis, we have the distance. So in work, energy, and power, we have delta EK and we have delta x. So we need to find a relationship where on the y we have delta EK and then on the x we have delta x. From the work energy theorem, right, 5.1 is hinting us on what we need to use. From the work energy theorem, we know that work net is equals to EK, but we also know that the work net is equals to F net multiplied by delta x multiplied by cos of theta, right? So EK is equals to F net multiplied by delta x multiplied by cos of theta. In our situation here, cos of theta, theta will be 0, right? Because you can see the force that is being applied, that is horizontal. So we're going to have delta EK being equals to F net multiplied by delta x. Cos of theta, if theta is 0, that will be 1, right? Because cos of 0 is 1. So we just have delta EK being equals to F net multiplied by delta x. So now we have EK on our y, and then we have F net as our m, right? Our gradient, and then we have the distance as our x. So here clearly the gradient or the slope will be giving us F net. So here you come and say F net will be our gradient, which we're gonna find by saying the change in EK divided by the change in distance or the change in x. Yeah, this is honestly a very strange question. I've never came across anything like this before I came across this question. Anyway, let's move to 5.3. 5.3 says, calculate the net force experienced by the object in the third region between 10 meters and 10 meters. So F net, we know that we're supposed to find delta EK and delta x, right? So we have F net being equals to EK final minus EK initial divided by, so that's divided by x final minus x initial. So that will be equals to, so we want the net force experienced between the region 10 to 15, right? So for x final, we're gonna have 15 minus 10 because that's our initial, right? Now let's find the corresponding EK values at 10. So if this is 2, if this is 4 here, then this is 2, and then this is 6, and this is 8. So 10 is here. So let's go up and see where 10 is. So 10 is somewhere here, and then now let's look at the y-axis and see how the box is and the numbers are pairing up. So if we have 40 and here we have 80, so here we have 60, here we have 20, here we have 100, right? So between we are between 80 and 100. So for EK 1 or EK initial, we have 90, right? Now let's come to EK final. So this is 10, 12, 14, so 15 is somewhere here. So let's go up and then let's see where we end up. We end up at around, so this is 160, so this is 180 here. So we have 180. So 180 minus 90, that is 90, right? And then 15 minus 10, that is equals to 5. So 90 divided by 5 is equals to 18, right? So F net between 10 and 15 is 18 newtons. Now let's move forward and do 5.4. 5.4 says, hence determine the magnitude of the force of friction experienced by the block as it moves over the third region. So force of friction. So we know that F net is equals to F1 plus F2 to some Fn, depending on the number of forces you have, right? So on that region, 10 to 15, we know that the F net is 18 Newton, right? So we have force applied minus friction. We say minus friction because it opposes the motion, right? So we're going to have 18 being equals to what's F applied? We are told that F applied is 30 Newton. So we have 18 equals to 30 minus Fr. So if we take 30 to the other side, we get minus 12 is equals to minus friction. So this will give us a frictional value of 12 Newton. Then that's 5.4. Let's move to 5.5. 5.5 is saying which region, first, second, or third, offers the largest frictional force. So again, we know that F net is equals to F applied minus Fr, right? One thing, the steeper the slope, the greater the value of F net, right? And then F applied is kept constant. So basically, friction is the one that is determining the steepness of the slope. So where the slope is the steepest, then we have less friction, right? So let's look at our graph here. From 0 to 5, it's pretty much steep, but then from 5 to 10, it's a bit gentle, right? And then 10 to 15 is also very steep. So 5 to 10 is gentle compared to the other parts, right? So there we have the largest friction. So here we're gonna say the second region has the largest friction. I hope you can understand that. And then 5.6 says explain your answer in question 5.5 without any calculation. That's basically what we just did, right? But then another way of doing, we can actually do the calculations, and you're supposed to get a frictional force that is less than that of the region 0 to 5 and the region 10 to 15.